In case of theory of pharmaceutical suspensions, the factors influencing the settling, uh, the Brownian movement is also a factor which influence the settling, which is also called drunken work. The Brownian movement of particles prevents the sedimentation. In general, particles are not in a state of Brownian movement in suspensions due to larger particle size and higher viscosity of medium. Brownian movement can be observed if the size of particles is about 2 to 5 micrometer and provided densities of particles and viscosity of a medium are favorable. So, theory of Brownian movement proposes particle size and viscosity as a major factors which can be defined by the Stokes law. Previously, we have covered these things. The rate of sedimentation equals to d square rho of dispersed medium or density of the dispersed medium minus density of continuous medium into gravitational force divided by 18 into viscosity of the dispersed medium. Sorry, viscosity of the dispersion medium. From this equation, uh, we can from this equation we can justify it by the we can justify the size of the particles, the densities of the particles, the viscosity of the medium, uh, which are favorable for Brownian movement. Next, the electrokinetic property. In case of electrokinetic properties, zeta potential is there. Zeta potential is defined as a difference between the potential between the surface of the tightly bound layer, which is called a shear plane, and electronatural region of the solution. Okay, and the flocculating agents. The flocculating agents decreases the zeta potential of the suspended charged particles, thus causes aggregation or flock formations of the particles. Examples of flocculating agents are natural electrolytes such as potassium chloride solutions or sodium chloride solutions and calcium salts, alum, and citrates, sulfates, phosphate salts, natural electrolytes like NaCl, KCl, etc. There are some important characteristics for flocculated suspensions and deflocculated suspensions, which we have already discussed. For flocculated suspensions in this system, particles resides at the secondary minimum, and they are separated by about 1000 to 2000 angstrom. Hence, the particles are loosely structured. Even in this state, particles experience a higher energy barrier but easily dispersible or easily redisperse. The particle-particle interaction are also influenced by the factors such as ionic strength, pH, size, and valency of added electrolytes, thickness of electrical double layer, etc. Particles in the suspensions are form loose agglomerates. Flocks are a collection of particles, so rate of sedimentation is high, and sediment is formed in the flocculated suspensions so rapidly. The sediment is loosely packed as the flocks are formed, so packing arrangement is loose. Particles are not bounded tightly to each other, so hard cake cannot form. That's why it's redisperse very quickly by mechanical shaking. The sediment is easily redisperse by small amount of agitation or small amount of shaking. The flocculated suspensions exhibits plastic or pseudoplastic behavior. Most probably these things you have already covered in rheology, the what is plastic flow and what is pseudoplastic flow. The suspensions is somewhat unsightly due to rapid sedimentation and presence of an obvious clear supernatant region. Here in this picture, we can show, we can see that these things are clear for flocculated suspensions. The pressure distribution in this type of suspension is uniform at all places. Therefore, the pressure at the top and the bottom of the suspension is same. Uh, in this type of suspension, the viscosity is nearly same at a different depth level. The purpose of uniform dosage distribution is fulfilled by the flocculated suspensions, but not totally. Uh, but uniform dose can be distributed, can be fulfilled for these flocculated suspensions. Now, the characteristics of deflocculated suspensions. In this system, particles carry a finite charge on their surface. When the particles approach each other, they experience repulsive forces. These forces create a higher potential barrier, which prevents the aggregation of particles. This state is observed in a deflocculated system, primary minima, where the sedimentation of particles is very slow. During storage, the deflocculated particles exhibit sedimentation owing to its size and density, although it is slow. The particles form a close packing arrangements wherein the smaller particles fill the void between the larger particles. As the sedimentation continues, the lower portion of the sediment get pressed by the weight of the sediment above. Clear? This force is sufficiently to overcome the high energy barrier. Once this energy barrier is crossed, the particles come in close contact with each other and established stronger attraction forces. This leads to the formation of a hard cake in deflocculated systems. Is this clear to all? The redispersion of this type of sediment, which have already formed a hard cake, is too difficult because enough work has to be done in order to separate the particles and create a high energy barrier between them. Therefore, agitation of the suspension is not adequate to redisperse the sediment in the deflocculated system. But for the flocculated suspensions, as the hard cake is not formed, only flocks are forming loose aggregation or loose sedimentation, so it can be easily redispersed by mechanical shaking.